Hello students, welcome to Educate. Today we are going to study numericals on chapter Gravitation. Question number 1. Answer the following. You can shield a charge from electrical forces by putting it inside a hollow conductor. Can you shield a body from the gravitational influence of nearby matter by putting it inside a hollow sphere or by some other means? If you have a conductor like this and there is space inside, if you give charge Q to it, then what will happen? The effect of charge inside will be zero. Here there is no electric field. If you put some electrical instrument, that is if you put some instrument that is sensitive to electric field, so that will be protected inside, because there is here E will be zero, means there is no electric field. Outside there will be electric field. So this type situation is called electrostatic shielding. Electrostatic shielding. Now our question is whether gravitational shielding is also possible. Gravitational shielding means if there is one object, it will be attracted by Earth. Now, can you put something here which can prevent it from being attracted by Earth? So that is not possible in any case. Electrostatic shielding is possible, that you have seen, but here gravitational shielding is not possible. Second question. An astronaut inside a small spaceship orbiting around the Earth cannot detect gravity. If the space station orbiting around the Earth has a large size, can he hope to detect gravity? Of course, if size will be large, in that case there must be some gravity. Then if you compare the gravitational force on the Earth due to the Sun to that due to the Moon, you would find that Sun's pull is greater than the Moon's pull. You can check this yourself using the data available in the succeeding exercises. However, the tidal effect of the Moon's pull is greater than the tidal effect of the Sun Y. So, general formula of force, gravitational force is F proportional to 1 upon R square. But as far as tidal effect is concerned, so tidal effect depends on third power, RQ, right? So if we compare force due to Moon divided by force due to Sun, so we will get here distance R Sun whole cube divided by R Moon whole cube. Definitely this value is very large as compared to this value. So corresponding value you will get that Fm will be larger than Fs. So that thing they want to tell you here. So I think you have understood. Next point. Choose the correct alternative. Acceleration due to gravity increases or decreases with increasing altitude. If you remember, I told you the formula for GH. GH equal to G times R divided by R plus H whole square. If H increases, then definitely this will decrease. So for any value of H, denominator will be larger. So this value, this is acceleration due to gravity on Earth, will decrease. So you can say GH is less than G. Now, acceleration due to gravity increases or decreases with decreasing depth. G depth is given by G times 1 minus D upon R. Here again, when you put some value of depth, in that case, overall value will decrease. So you can say GD will be less than G. The acceleration due to gravity is independent of mass of the earth or mass of the body. If you remember the formula for acceleration due to gravity, Gm upon r square. Here m is mass of earth, this is radius of earth. Mass of object is not involved in the formula. So definitely our answer will be acceleration due to gravity is independent of mass of the body. Then next point comes the formula minus Gm, the formula minus Gmm 1 upon R2 minus 1 upon R1. This is for potential energy. Another formula Mg R2 minus R1. This is another formula. So here question says which one is more accurate. Here small g is involved and you know small g varies. So there will be variation in it. But here small g is not involved. So there won't be variation. So accuracy in this case is more than this. Next question is, suppose there existed a planet that went around the sun twice as fast as Earth. What would be its orbital size as compared to that of the Earth? Here, what is basic concept? K plus formula, I think you remember, T square proportional to R cube, where T is time period, R is measure of semi-major axis. Semi-major axis, I think you remember, this is major axis. If you take half of it, this is case of ellipse. So T square proportional to R cube. Here question says, suppose there existed a planet that went around the sun twice as fast as the Earth. So time period of planet is time period of Earth divided by 2. So what would be its orbital size as compared to that of Earth? So let's see. We can write R planet cube divided by R Earth cube will be equal to T planet square divided by T Earth square. Same thing I have written here. Our concern is to get R planet. Right. So do one thing, just write R planet whole cube equal to T planet square divided by T Earth square times R Earth cube. Right. Now do one thing, take cube root. So you will get R planet R planet equal to R Earth. Then T planet we can write TE by 2. So TE by 2 TE whole power 2 by 3. Did you understand? Here cube root is taken. So power is 2 divided by 3. So this will give R planet equal to R Earth times 0.5 power 2 by 3. Now if you are given RE, 1 astronomical unit, you know distance between Sun and Earth is 1 astronomical unit. This is around 1.5 into 10 to the power 11 meter. So that value can be put to get RP. I think thing is clear. Okay. Now I0, one of the satellite of Jupiter has an orbital period of 1.769 days and the radius of the orbit is this much. So that the mass of Jupiter is about 1000 that of the sun? This is a really good question. So okay, so if you remember, m is given by 4 pi square divided by g r cube divided by t square. If you have doubt why this formula, so I can tell you that suppose this is situation, this is m, this is say small m. So force between the two, F will be GMM divided by, say this separation is R, so R square. Also centimeter force, F is given by mv square upon sorry. So F equal to mv square upon R. If you equate the two, what do you get? GMM divided by R square, so make it also R, so here, so equal to mv square divided by R. One R will cancel out from here, one M will cancel out from here, so you will be left with GM. Let's write afresh, so it will become better for you. So here we have equated G capital M small m divided by capital R square equal to m v square divided by capital R. 1m will cancel out and 1r will cancel out, and the v equal to, you can write v equal to 2 pi r divided by t. So what will it become? Gm divided by r equal to 4 pi square r square divided by t square. Our concern is to get m. So m equal to, here r will become r cube, 4 pi square divided by t square, and then g will be here and r square. So 1 r will make it r cube. So you have got m equal to, you can write like this, 4 pi square upon g times r cube divided by t square. So this formula we are going to make use for two planets we will consider. One, the planet of, here the satellite of Jupiter, to get mass of Jupiter, and then we will make use the Earth and the Sun also, and we will see how they are related. So let's write mass of Jupiter. So 4 pi square divided by capital G times r, let's write it, this distance, it is given as this 4.2 to 10 power 8. So we denote it for time being as r Jupiter, and then we write it cube divided by time Jupiter, let's write it, and write square. Later on I will put the values, and here we are writing this mass for, we are talking about Jupiter, so let's write this mass Jupiter, right? Then for mass Sun, in that case again same thing, we will write 4 pi square upon g, then distance between Sun and Earth, so let's denote it rs, divided by time period of Earth around the Sun, so let's write it time Sun. Notation you can also write as E, that does not matter. So here we have to make comparison between the mass of the Jupiter and that of the Sun. So do one thing, just write the ratio of the two, mass Sun divided by mass Jupiter. Then what do you get? If you divide these two, so these two terms will cancel out, this will remain here, r Sun square divided by t Sun square, right? Then here this will go in denominator, r Jupiter square, Here 1 is in cube, our sun is cube. So this will be in cube, and T Jupiter square, right? I think up to here there is no doubt. Let's put the values. R sun means distance between sun and earth. So that is 1.5 into 10 to the power 11 whole cube. Alright. This is time taken by the satellite of Jupiter, 1.769 days. So just write 1.769 divided by here time taken by Earth. So 365 days, and then whole square, whole divided by here our Jupiter, separation between Jupiter and its planet is 4 point, not planets, separation between Jupiter and its satellite 4.22 into 10 to the power 8 whole cube. Now if you simplify, it will come about around 1041. This is exactly 1041, which can be roughly written as 1000. That is why is about 1000 that of the sun. So this is the case. Think is clear? Now next question. Let us assume that our galaxy consists of 2.5 into 10 power 11 stars, each of one solar mass. How long will a star at a distance of 50,000 light year from the galactic center take the complete one revolution, take the diameter of the Milky Way to be 10 power 5 light year? So in this question, total mass, say mass equal to number of stars. So 2.5 into 10 to the power 11 into each star has one solar mass. So mass of sun 2 into 10 to the power 30 kg. Now what is the distance? Distance is given as here R is given as 50,000 light year. So we have to write the value of 1 light year, although you know how to evaluate 1 light year. 1 light year means distance traveled by light in 1 year, that is 365 days into 24 hours into 60 into 60, this is number of seconds in 1 year, then speed of light 3 into 10 to the power 8. So this will be equal to 1 light year, so it will be around 9.46 into 10 to the power 15. Let's confirm it, then we will proceed. Yes, so it is 50,000 into 9.46 into 10 to the power 15 meter. So we have got M and R. Now what do we want to find out? We have to find out the time period. So the same formula we can apply. So M is equal to 4 pi square upon G, then R cube divided by T square. Here our concern is to get time. So T square is 4 pi square upon Gm multiplied by R. Let's put the values. So 4 pi square, 4 into, it will be around 9.8, pi 3.18, 3.14 square into r is this much. So 50,000 into 9.46 into 10 to the power 15 whole cube. Divide by value of g. G is 6.67 into 10 to the power minus 11 into mass of this. It will be 5 into 10 to the power 30 and 11, 41. Now take 1 minute to evaluate and then take square root. Okay, after evaluation, you will get certain number of seconds, that is your task. And if you want to convert that into year, that value, so this is t square. You have to get square root, then you will get this value in seconds. And to convert this value into year, you have to divide by number of seconds in 1 year. So 365 days into 24 hours into 60 into 60. So you have to divide by this value to get number of years, and answer is 3.58 into 10 to the power 8 years, I think. So answer will be this. Calculation, I think you know how to calculate. Here third power is there, 10 power 45, this will become, here this is 10 power 41, here minus 11, so this will become 30. Try to do it. Now, next question says, let us assume that our galaxy consists of this much. No, it is done. Next question is, choose the correct alternative. If the zero of potential energy is at infinity, the total energy of an orbiting satellite is negative of its kinetic energy, potential energy. So we have already studied that if kinetic energy is x, then potential energy will be minus 2x and total energy will be minus 2x plus x, that is minus x. So what do you observe? Kinetic energy positive, potential energy, total energy negative, but equal in value, and the potential energy is just double of kinetic energy with the negative sign. So here question says, if the zero of the potential energy is at infinity, the total energy of an orbiting satellite is negative of its kinetic energy, potential energy. So total energy is here negative, kinetic energy plus x and total energy is minus x. So answer will be kinetic, these two are related. So it will be, total energy will be negative of its kinetic energy. Expression I am not writing, that you have already studied. So the energy required to launch an orbiting satellite out of Earth's gravitational influence is more or less than the energy. So situation is like this. Suppose this is Earth, here there is satellite. So this satellite has orbital velocity VO equal to root GR if H is less. If you go to original formula, so it is GM divided by R plus H. So here, if you, this is orbital velocity, and if you want to give make satellite free from Earth's gravitational pull, then you have to provide V escape. If you know the relation, V escape is root 2 GR. So relation is V escape equal to root 2 times V orbital, right? So just give increase the velocity root 2 times, from here it will escape. And if object is here or projectile is here and you have to project, then more energy will be required. So here our question says the energy required to launch an orbiting satellite out of Earth's gravitational influence is less than the energy required to project a stationary object at the same height. So if you want to project from here to here, so in that case, just in terms of velocity you can consider, for orbiting satellite the velocity is around 7.92 kilometer per second, right? Just make it to 11.2 kilometer per second to escape. It will escape from Earth's gravitational pull if this velocity is attained. So there is slight increase, but if here planet is here and it has zero velocity, then you have to give this object this much velocity to reach over there, to project itself in the orbiting path, in this path. So we have observed that it is easier to make a satellite escape from the Earth's gravitational pull than to put it into motion in certain orbit. Now, next question is, does the escape speed of the body from the Earth depends on mass of the body, location, the direction of projection, height of the location? So here in formula, V escape either root 2gr or original form if we write 2gm divided by r plus h. Here, what do you observe? Mass of the body is not there. This is mass of the Earth here, and direction of projection theta is not involved at 45 degree, at 30 degree with the horizontal, whatever. If you are projecting like this, if you are projecting like this, if you are projecting like this, so these angles are not involved in the formula, so you don't have to care about it. Then comes height of the location. Yes, h is involved. If it is already at certain height, then this value will decrease. So you can say that escape velocity does not depend on mass, does not depend on projection direction, but it does depend on height. Okay. Now, next point. Question number 7.8. A comet orbits the sun in highly elliptical orbit. Does the comet have a constant linear speed, angular speed, angular momentum, kinetic energy, potential energy, total energy? Okay, many concepts are involved here. If you remember, the orbit is like this and sun is suppose here. When planet is here, then it will move slower because aerial velocity is constant. But when planet is here, then its speed will be faster. For same time interval delta t, planet will cover from A to B, and for same time it will cover C to D. So what you have observed here, speed is faster. Here suppose Vp, here say Va. So obviously Vp will be faster, and V is related to angular velocity also. If V is changing, then omega will also change. So in our question, it says, does the comet have a constant linear speed? Linear speed, so V is changing as you have observed here. Angular speed, that depends on V. So it will also change angular momentum. In planetary motion, if you remember, there is no external torque. If there is no torque, then L will remain constant, because dl upon dt equal to tau. And since tau is absent, then L will be conserved or L will be constant. Then next comes kinetic energy. It depends on velocity, so it will change. Potential energy, it depends on position, it will change. Total energy, it will not change. So I think you have understood. Now, there is next question. Which of the following symptoms is likely to afflict an astronaut in space? A. Swollen feet. B. Swollen face and headache or orientational problem. C. Gravity will be less. So if feet are swollen, so that does not matter. But swollen face, it will affect because blood will move up. Headache will affect. Orientational problem, of course, it will. So except the first one, swollen feet, others are possible. Question number 7.10. What does it say? It says in the following two exercises, choose the correct answer from among the given ones. The gravitational intensity at the center of heavy spherical shell of uniform mass density has the direction indicated by the arrow A, B, C, etc. And for 11th question also same thing. For the above problem, the direction of the gravitational intensity at any arbitrary point P. So this is the point. So these two cases we are going to see. If you remember, if there is a sphere of uniform density and if you take any point here or here, in that case you will see that gravitational field intensity will be 0 here because of symmetry. But if upper portion is removed, then this intensity will be in the direction of heavier portion or in the direction of greater concentration of mass. So in both the cases, in question number 7.10, that is this point, so intensity will be like this. At this point, intensity will be like this. Is it okay? Now, let's see question number 11. What does it say? We have already discussed. Question number 12. A rocket is fired from the earth towards the sun. At what distance from the earth's center is the gravitational force on the rocket is 0? Mass of the sun is given, mass of the earth is given, and orbital radius is given. So this question is simple. They are saying that this is earth and suppose this is sun. Read the question once again. A rocket is fired from earth toward the sun. At what distance from the earth's center is the gravitational force on the rocket at 0? So this is earth and this is sun. Suppose this distance is x. Total distance is r, so r minus x. And suppose this is neutral point, so you can say mass of earth, mass of sun. So force at this point should be 0, so we can write g times mass of earth, mass of rocket divided by x square must be equal to g times mass of sun, mass of rocket divided by r minus x whole square. So gm will cancel out. Mass of earth 6 into 10 to the power 24 divided by x square equal to mass of sun 2 into 10 to the power 30 divided by r minus x. R is given or something is given, orbital radius, yeah, Orbital radius means this thing. R is given. R you can take 1.5 into 10 to the power 11. So first write here x square, and in the next step we can write it. So here 2, 3, and here 10 power 24. So 10 power 6 will be left. Right. Now keep in mind, unit of R and X must be same, otherwise your subtraction will not be possible. So let's write it. So what we have got here, I'm rewriting G mass of G M mass of Earth divided by X square must be equal to, it is G M sun small m divided by R minus X whole square. So here this 10 power 11 you should not consider for making calculation. Just take R equal to 1.5. Later on we can add that value. So calculation will become easier. Or if you take that value 10 power 11, then here also you have to write, because R and X must be in same unit, otherwise subtraction will not be possible, or if it will be possible it will create difficulty for you. So G cancel out, mass of Earth, that is 6 into 10 to the power 24, m will cancel out, and then X square equal to, take care mass, this will become, this is 2 into 10 to the power, how much, 10 to the power 30, and divided by, this is 1.5 minus X whole square. Now what do you get? So 2, 3, 10 power 24, so 10 power 6 will be left. So X square times 10 power 6 is equal to 3 into 1.5 minus X power whole square. Just have a look, 1 minute. If you take square root here, what do you get? So this will become X into 10 power 3 equal to, this is root 3 multiplied by 1.5 minus X. If you simplify, what do you get? So if there will be problem, I will tell you other way around also, don't worry. But everything is correct up to here, so nothing to worry. So here this is 1000 X equal to root 3 into 1.5 minus 1.73 X. Take this value here. So it will become 1000 1.73 X equal to 1.732 into 1.5, and then X will be equal to 1.732 into 1.5 divided by 1001.73. Right. So you will get this value, whatever value you are getting. So that value will get multiplied by 10 power 11. You have understood why? Because that power I have not taken into consideration while calculating the value. So if you evaluate it, it will come out to be 2.59, means final value after multiply this. So 2.59 into 10 to the power 8 meter. So this is how you can solve it. So we have solved till question number 7.12. So in this video, I think you have enjoyed. We will continue with the next video from 13 onwards. Thank you for watching. Team Education